In Chapter 1, we look at statistical basics. So we're going to get some nomenclature, some definitions, kind of look at some basic kinds of things that we do in statistics. And then we'll actually take off from here and actually begin to do some statistics. As we have here, statistics is the scientific path from data to knowledge. I like how it says that. It's a process that gets us from taking information, well, not information, it becomes information after we process it. When we start, it's just data. Okay, it's just data. And then somehow we have to follow this process, or we can follow this process that we'll show you, or I'll show you, that will convert the data and organize it so that it becomes information that we can actually use, usable information. Let's see, I think I can make this a little larger. I can run it as a slideshow here. Yep, okay. So what is that journey from data to knowledge? Statistics is the study of how to collect, organize, analyze, and interpret data collected from a group. Okay? So we collect, step 1. 2, we organize. 3, we analyze. And 4, we interpret. And then in that process, we then take raw data in, and after we're done interpreting that data, then we have information, usable information that we can use in our lives, in our businesses, etc. There's 2 branches of statistics. There's descriptive statistics. With descriptive statistics, that is the collect and organize steps or stages out of the 4 steps here. So we first collect and then we organize the data, and that's what descriptive statistics is about. And that's what the early part of the textbook is. Chapters 1 and 2 and 3 basically are all about descriptive statistics. And then we'll transition from the descriptive statistics, really hitting it, the inferential statistics anyway, in Chapter 7 and beyond, where we get into actual analyzing and interpreting the data. So first 3 chapters will be descriptive statistics, and then 7 through 9 that we cover will be inferential statistics. Stuff kind of in between sort of lays the groundwork for kind of understanding inferential or statistics, or the basics, I guess. Well, the base, I think that's a good word for it. Gives us a better sense of the base or the foundation on which inferential statistics sits. I think maybe that's a good way of making a metaphor for it. Okay, in 1.1 we're going to look at some key terms. When we look at wanting to set up a study or an experiment, then these are some key terms that are going to pop up that we need to be able to identify. And so we're going to start with these key terms, and then we'll practice a little bit on how to kind of identify in a situation what is the individual, the variable, the population, the sample, the parameter, and the statistic. So an individual, first term, is a person or object that you are interested in finding out information about. I think of the individual as the who or what that we want to get information from. Okay, it's the who or the what that we want to get some kind of information from. The variable, or also known as a random variable, this is the measurement or observation of the individual. So the variable is the actual measurement that we get. It's the data that we actually collect from the individual. So maybe an individual is a person in our classroom, and we want to find out how tall they are in inches. And so we'll go ahead and measure that individual's height. So their height in inches, maybe for example 65 inches, then that would be the variable would be the 65, which is the measurement that we get from the individual, maybe Joe or someone. So the individual would be Joe, that individual, but the 65 is the measure, the variable that we are collecting from that individual. The population is the set of all individual measurements about which we are interested. I changed this a little bit from the original slide because I think it was a little bit confusing, or confuses students. It confused me, I think, the way it was originally written, because I want to be clear about what the population looks like. Okay, it's the set of all individual measurements. So I wanted to emphasize here with this definition that it's not the individual that is in the population, it's their variable, the measure that's in the population. So for example, in our class again, if we say we have 30 students in the class, and we take each student and we measure their height in inches. So the population is not going to be a collection of a bunch of names. That's not what the population is. It's not the actual individuals that are the population, but this would be a set of actual numbers, which would be their height in inches. So instead of having a set with Joe, Sally, and Kim, or Jose, or whomever might be in class, it's going to be a list of maybe 60, 72, 59, let's see, maybe 71, 68, 67. So it's going to be a set of numbers. Okay, so the population is not the set of the individuals, it's a set of the variables that are measurements from those individuals. Okay, we want to be very clear about what the population is. It's a set of measurements, variables. Now, a sample is a subset from the population. It looks just like the population, but it contains less data. So it's just kind of like reaching in to a big pot of things and pulling some out. Okay? And that kind of a metaphor literally is a subset, or just a group from a larger group that is the population. So for example, in our class, if we're only looking at the individuals in our class, and there's 30 individuals in our class, and we measure their heights, then the population is going to be the set of 30 numbers that represent the heights of those individuals. And then if I want to take a sample from that population of 30 students, maybe I just grab 5 students from that set of 30. And again, not the students, but their measures. So I'd have a subset that might look like 58, 73, 65, and a couple other numbers thrown in. So it's just a subset that comes from the bigger set from the population. Now when it comes to actually kind of thinking about this in usage, if we have a small population that we're interested in, we might want to get measurements or variable kinds of data from individuals from every member of that population. So if we only had the class, I'd probably go ahead and just grab all 30 individuals, because it's not that big of a group. And then we'll go ahead and make some kind of computation or some kind of study about those numbers to see maybe what the average height is, and what the spread is, what kind of variability is there in terms of the height in inches. That would be what we call a census. So if you take everyone in the population, then you're really taking a census. You're not really grabbing a sample. You use everyone in the population. We call that a census. And later we're going to get into how to do proper sampling. But if you get a subgroup, something smaller than the whole population, then that's the sample. And let's see, where was I going with that? Let's see. Oh, well, it's just called a sample. That's it. It's not that different from a population. It's a census, and then when we grab out a sample, it's called a sample. Okay. All right. Now, a parameter is a number that is calculated from the population. This number is fixed. It's unknown, that we want to find out about, or we want to find it. So let's say I want to find the average height in inches of our class. So we take all 30 students, find their height in inches, add them up, divide by 30, the number of students we have in class. Then that would give me the average height in inches for our class. And that's called a parameter. And a parameter is something that we calculate using the variable measurements that come from individuals. So what we do is we take the numbers, or the variable, whatever the variable measures are in our population set, we take all of those and we do a computation on it. And that computation is the parameter. So the parameter is a calculation that we make on the data that's in the population, the set that's called the population. Now sometimes in situations it's not easy to find or get your hands on a whole population. For example, if we wanted to look at the average height of all Americans, or all people in the United States, that's a rather daunting task. Over 320 million pieces of data, measurements, that we'd have to grab and then average out. So there, rather than doing a census, we'd probably want to do compute a statistic by taking a sample, a subset of people in the United States, and then find that subset, all the heights from that subset or sample that we take, and then do the average on that set, which is a smaller set from the sample, or the sample data. And so the statistic, finding the average, it's still the same computation, but we're going to use the numbers, or whatever the data set is, in the sample rather than the population now. And so we take those numbers in the sample, add them all up, and divide by how many there are in the sample. So it's the same computation, finding an average. It depends on what set of numbers you use, or what set of variable values you use. If you grab the population values and do the computation on that set, it's called a parameter. The computation, if you use the values that are in the sample set, then that's called a statistic. So it's the same thing. In both cases, we're computing an average height. But in the first case, we call it a parameter because it's for everyone, the whole population, and we call it a statistic, that average, because we're applying it to a sample. And the reason we might want to do that, again, is maybe it's too hard to get a census, to get all the population, the data from all the population. And so we take a subset, and then we make compute a statistic on that subset, and then we make an inference about the sample, the subset, that we can then infer to about the entire population. So that's when we get into inferential statistics, is we'll take samples, we'll study the samples, make inferences about the greater population, from this sample. And then, of course, we'll get into it in 1.2, how to do sampling so that it gives us the best chance of coming up with an unbiased sample. And another idea that we're often interested in, for example, with polling kinds of data, we want to make sure that our sample is representative of the greater population. So you want to get a sample that sort of has the same makeup as the greater population, so that you're not maybe skewing it one way or the other because maybe you over sampled people with a certain characteristic, for example. So we want it to be representative of the greater population. Now there's a couple of types of variables. Remember that second step, individuals, and then variables. Individual is who or what we're getting the data from, and the variable is the data that we're collecting from that individual. So the variable can come up with different kinds of values. Okay. So one type of variable values that we can collect for a population or a sample is qualitative or categorical variables. In this case, the answer is a word or a name that describes a quality of the individual. So if you are grabbing some kind of information or data from an individual, if that data that you're collecting is descriptive, so it's a word or a name that describes something about that individual, that person or object that you are interested in, then we call that qualitative or categorical data. So it'd be a qualitative or categorical variable. Quantitative or numerical variables or data. Here, the kinds of information we're plucking from the individual is going to be a number, something that can be counted, or a measurement from the individual. So if it's a number, it's probably quantitative, unless it makes no sense to do arithmetic on it. So there may be situations where numbers aren't necessarily quantitative, and we'll see some examples of that. Knowing whether you have qualitative or quantitative, categorical or numerical data, if your variable spits out those kinds of values, will make a difference in terms of what kinds of computations we can actually do with the data. So if we have qualitative data, then there are certain things that we can't do with it that we could if we had numerical data. And so knowing what kind of values the variable is going to give us is helpful in terms of what we could do with it in our process. Examples of qualitative data that could come from a qualitative variable would be the color of a car, for example, or the eye color or hair color from people, or the type of car that maybe is in a parking lot. If the parking lot is our population that we're interested in, or the types of car that might drive under an overpass on a freeway, you take a look and you just record the car make. So those are words that are used to describe. If we want to look for quantitative, then we're looking at some kind of a count or a measurement. So how many things do we have, or how many people that have this quality that we're looking for? Or again, like the example with the class and the height. So the measurement in inches of the height for the individuals would be quantitative type of data. Let's see, before we get into, or no, I wanted to get into this next. Let's see. Actually, I think I wanted to skip over the types of variables and just get to this, because this is kind of an awkward screen. It sort of separates from the individual variable population sample parameter statistic information. Then it's a little jarring. We'll get more into these types of variables later. So I wanted to just skip that slide for right now and come to this slide, where this is an example of, given a situation, a scenario, can we identify the individual, the variable, the population, the sample, the parameter, and the statistic. So sorry about that. I spaced out and hit that slide when I intended to skip it. Now, anyway. In 2010, the Pew Research Center questioned 1,500 adults in the U.S. to estimate the proportion of the population favoring marijuana use for medical purposes. It was found that 73% are in favor of using marijuana for medical purposes. State the individual, the variable, the population, the sample, the parameter, and the statistic. Now, oftentimes, to identify those different classifications, I guess, I often like to start with the parameter or the statistic, which is the calculation, the computation. What is it I'm trying to calculate? Because if I know what I'm calculating, then I know what kind of data I'm going to be using in that computation, and then that tells me whether or not I have a population or if I have a sample. And it also helps me identify then what the variable is, and then what the individual is. So for me, going backwards through the list, I think, is actually a little bit easier than trying to start at the top and identifying who or what the individual is. So for example, here in this case, I see that we want to compute a proportion. Okay, so if we want to compute a proportion, then I think about, how do I make that computation? What in the world am I going to compute? Well, I'm going to need to compute the total number of responses for the denominator, and then in the numerator I compute the number of individuals that have the characteristic that we're looking for. And then that tells me the proportion of people who, in this case, what we're looking for is, does an individual favor marijuana use for medical purposes? So to do that, I got to get counts of the total number of individuals, and then we also have to grab the out of that the number of individuals who favor. So we're going to be looking at some kinds of responses here. We'll count the number of responses, but the data that we're going to collect isn't going to actually be numerical. We're not collecting numbers, but we're going to collect the responses that people have to this question. And what kinds of responses could we get? Well, some people would say, yes, I do favor, and some people would say, no, I do not favor. So what we're actually collecting here are a bunch of responses, a bunch of yeses and nos. So we're collecting qualitative data in this case, words, responses from individuals. And we see that we have, in the research center, they questioned 1,500 adults. So that's not everyone in the U.S. So that's obviously a sample that we're working with. And so we're finding a proportion of a sample. So that tells me, well, tells me that we're working with a sample is what I'm trying to say there. In my mind's eye, how I envision this then is the sample is going to be a set of yeses and nos, and there's going to be 1,500 yeses and nos in that set. And then I'm going to count up how many yeses are in that set. and divide that by how many responses, 1,500, there are. And then that makes my proportion. So again, thinking about how I'm going to do the computation kind of helps me visualize a little bit what does the population or the sample look like. In this case, sample, I see it's a set of yeses and nos. And since in the set is a bunch of yeses and nos, then I know the variable is going to have to be the responses of the individual adults to this question. Okay, so the variable is quantitative or qualitative, and it's a yes or a no. The individual then has to be the U.S. adult that we're going to be asking the question, do you favor marijuana usage for medical purposes? That's who we want to get the yes or no from. And so knowing what the variable is helps me figure out then, well, what am I going to get that yes or no from? Who am I going to get it from? And in this case, it's a U.S. adult, because our sample was from adults in the U.S. And I think that's pretty much what the author has here. The individual is a U.S. adult. The variable is the response to the question, should marijuana be used for medical purposes? Population is the set of all responses of adults in the U.S. So that'd be a huge set of yeses and nos. I don't know how many adults there would be. You know, maybe like 150 million yeses and nos. So that's a huge set of yeses and nos. And then the sample, of course, again, is just a set of 1,500 yeses and nos. Okay. Let's take a look at another example. A biologist wants to estimate the average height of a plant that is given a new plant food. She gives 10 plants the new plant food. State the individual, variable, population, sample parameter, and statistic. So in this particular case, we are computing the average height. So to compute an average, I have to collect a bunch of numbers and divide by how many of them there are. And so I know that my variable's got to spit out quantitative data in this case so that I can compute an average. And height, estimate the average height, well, it wasn't stated what it's going to be measured in. Again, we could say inches or maybe centimeters or something like that, but somehow we'd have to come up with a unit of measure to get that average, or to get the average height. We'd have to have a bunch of heights that we could compute, use to compute. So again, to compute the average height, looks like we're doing it on just 10 plants, so we have a subset. We don't have it with all the plants that are given this food. So we're just using a subset, so it'll be a sample. And so we're going to have a sample of 10 numbers that will be the heights of the plants that were given the new plant food. And then again, the variable is going to be a number indicating in inches or centimeters the actual height of the plant. And then we got to get it from an individual plant that was given this plant food. So again, that's kind of going backwards, trying to figure out, if I have a computation, then what kind of things am I going to be computing with to make this computation? What kinds of data can I have to make this computation? Does it have to be quantitative because it's a type of computation I couldn't do with qualitative, or is this something I could do with either? Those kinds of questions. Again, the author has the individual is a plant given the new plant food. Okay. From the individual, the variable is the information we're going to get from that plant is the height of the plant, and that's quantitative because it'll be a number that indicates either the height in inches or centimeters or whatever the units are. The population is the set of all the heights of plants when the new food plant or the new plant food is used. So again, that population would be very large. We'd have to look at the collection of all heights, so their numbers of plants that were given this new plant food. And that's too hard to get our hands on. Trying to figure out all the plants that have been given this food. So instead, we have a controlled sample here. So we only picked 10. And so our sample has 10 numbers that indicate the heights. And so if we were doing the parameter, we'd have to take all the heights of that big set, which could be, I don't know, thousands of plants that have been given this new plant food. But the statistic would be the average on just those 10, the subset of 10 plants that we picked out. And again, the sample then is a set of 10 numbers that mean the heights of those plants. So again, I want to emphasize, because students seem to have a hard time with figuring out what the population of the sample are relative to the individual and the variable. Too often students want to put in the population of the sample, the individual, rather than the variable. So again, it's a collection of measurements, not a collection of individuals. The population of the sample are collections or sets, groups of measurements that the variable can take on. Okay, and that's it for 1.1. The textbook exercises are problems 1 through 8, all of them. So 1, 2, 3, 4, 5, 6, 7, 8. So go ahead and give those a try. But before we go away, the person I get these slides from doesn't have quite as much information as another set of slides that I sometimes use from another instructor. Sometimes he puts in a few more slides. Well, between the two of them, the person I generally use the slides from will have the homework listed, which is nice, and they have examples oftentimes that the other person doesn't put into their slides. But I'm going to go back to types of variables, and there's a few extra slides that we can use from the other slide set. And so I was going to originally split off to this individual types of slides. There we go. Because they had a few extra slides when it comes to talking about the different kinds of or ways that we could break up qualitative and quantitative data, called measurement scales. So what kind of measurement scale do we have? So we can break the type of variables right now can be qualitative or quantitative. Now we're going to split those up a little bit more into nominal, ordinal, interval, or ratio types of data. And again, by analyzing and seeing what kinds of data we have, then it helps us to figure out what kinds of calculations that we can compute on that data. There's some things that we probably shouldn't do on some kinds of data that tend to be done, but maybe we shouldn't be making those computations. Nominal is data. Let's see, the data is just a name or category. Okay, that sounds a lot like qualitative data, doesn't it? And indeed, nominal data is a subset of qualitative data. So qualitative data could be nominal or could be other kinds of data, but nominal is one of those things that qualitative data can take on. Because it's just a name, it's a description. Okay, it's a description. It's It's not counting or measuring something, it's just describing it. There is no order to any data, and since there are no numbers, you cannot do any arithmetic on this level of data. Examples of this are gender, car name, ethnicity, and race. Okay? So car name, for example, if you have a subset of cars in maybe a parking lot that you're interested in, you would look to see what the make is. You know, it's a Honda, or it's a Ford, or it could be a Chrysler, or it might be a Mercedes, or it might be a Nissan, or a Tesla, or something like that. So we'd just get the car names as a description, or the color of the car. Be another nominal type of data. Ordinal is data that is nominal, but you can now put the data in some kind of order. So since ordinal is built on top of nominal, and nominal is data that is qualitative in nature, then ordinal is also qualitative data. The only difference between nominal and ordinal is that with ordinal qualitative data, you have some logical way of ordering the qualitative data that you collect. So both nominal and ordinal are qualitative data. So if you want to think of it as, okay, qualitative data splits off into subsets, nominal and ordinal. Okay, so qualitative is either going to be nominal or ordinal kinds of data. And then to go on with the ordinal, we can put the data in order since one value is more or less than another value. You cannot do arithmetic on this data, but you can now put data values in order. Examples of this are grades, A, B, C, D, and F, place value in a race, first, second, third, and the size of a drink, small, medium, and large. Okay? So those kinds of data are all really just descriptive. They're qualitative. Notice that the numbers first, second, and third, those don't indicate some kind of a count or a measurement. It's place is what it is. Numbers can have a couple of different qualities, or what they might represent, what kinds of qualities of objects that they might represent. One type of number we call in mathematics cardinal. They don't use that name here, but a number that is cardinal represents the quantity, how many things. So how many things are in a collection. So a count of things, or it might be measurement. Ordinal is when the numbers measure, or don't measure, but just simply indicate place. Okay? So numbers can be ordinal numbers, or they could be cardinal numbers, and ordinals are just all placeholders. Now I also think of, when it comes to these kinds of ordinal numbers, or not numbers, but the ordinal data, then oftentimes there's not a sense of, not a real defined sense of the distance sort of between, because they're just placed, like in a race here, coming in first, second, and third. If you're looking at a horse race, then first and second, it doesn't make any sense to try to take a difference between that, because the two horses might finish where one noses out the other, a very close finish. Or it could be that the first place horse is a bunch of different lengths, like 4 lengths ahead of the second place horse. And so it doesn't indicate any kind of fixed difference between what first and second means. It's could be a whole lot of things. It's not some kind of a standard. And so I think that may help to kind of if you have numbers, to help you figure out if they're ordinal numbers or if they might be the next variety, interval and ratio. Because the textbook talks about interval and ratio data as being quantitative. So just like we saw qualitative data split off into nominal and ordinal, we can see quantitative data being split off into interval and ratio. So interval data, okay, this is data that is ordinal, but you can now subtract one value from another, and that subtraction makes sense. You can do arithmetic on this data, but only addition and subtraction. Examples of this are temperature, like how warm or cold in Fahrenheit or Celsius is it outside, and time on a clock. Okay, so when you look at time on a clock, like 1 p.m., 3 a.m., 3:30, 5:30, p.m. or a.m., those times there are examples of interval data. They're quantitative, they're numbers, but they're as let's go ahead and talk about ratio, and then we can maybe come up with a sense of how it differs from interval. Why is that sense of time considered interval data? But certainly with these examples, you can take temperature in Fahrenheit or Celsius. You can take the difference of two, and you can get a sense of, well, how many degrees warmer or how many degrees colder is it. Same with time on a clock. Going from 1 p.m. to 3:30 p.m., then you know that, oh, an hour and a half, let's see, from 1 p.m. to 3, so 2.5 hours have passed, so we know what kind of interval of time we have. Okay, with ratio, the data, this is data that is interval, but you can now divide one value by another, and that ratio makes sense. You can now do all arithmetic on this data. Examples of this are height, weight, distance, and time. Now, what kind of time here are we talking about? Because we saw in interval, an example was time on a clock. Well, the time we're talking about here would be like how long it takes you to run a race, that kind of time. So it's not a clock time, but it's a time of how long it takes to do something. And so that kind of a number, like it takes you 15 minutes and 30 seconds to complete a certain kind of a race or a run, or how long it takes to do some activity. That kind of time is ratio data. And whereas time on a clock is not. And we can see, we can do more than just addition and subtraction on this kind of time. It makes sense. We can take, for example, all of the finishers in a race, and we can add them up and divide by how many. We can compute an average on that, and it makes sense. The average time it took for the participants to complete their run. But I think what clicks with me more than what's given here, that you can now divide one value by another and the ratio makes sense. I think in the textbook, the way they say it is in terms of an absolute or a relative scale. So with interval data, you have a relative scale. With ratio, it's absolute, and in particular, 0 is the key value in the context of interval or ratio that might help you identify whether you have interval or ratio data. With interval data, 0 is just another tick on the scale. It really doesn't mean anything that's any different from any other number that you might use, like on Celsius or Fahrenheit. So with a Fahrenheit scale, 0 degrees is just another tick mark. comparing it with 50 degrees. All it is just two different tick marks on that scale. 0 doesn't have a meaning in terms of an absence of something. And that's what happens with ratio data, is that the 0 represents an absence of something. And when you have that, then you're working with ratio data. So as an example, again, Fahrenheit or Celsius, I don't see as ratio. Those are interval, because 0 on those scales is just another tick mark on the scale. It doesn't mean an absence of anything. It's just a relative sense of hot or cold. However, if you look at the Kelvin scale, now that one is different, because 0 on the Kelvin scale, that absolute 0, is a lack of heat, a lack of motion, an absence of heat, or excuse me, an absence of heat or an absence of motion in the molecules. Okay? And so that represents an absolute 0. So I personally see the Kelvin scale then as ratio data, but Fahrenheit and Celsius I see as interval data, because there is no absolute 0 on those scales. It's just another tick mark. Okay. Maybe to pontificate a little bit further on this, these are things that kind of pop up in my head, like the grades here, A, B, C, D, and F. A lot of times what we'll do is give A a value of 4, B a value of 3, C 2, D 1, and F 0. So what if we convert those to numbers? Does that change it into something? Well, we're arbitrarily just kind of giving number values to the letter grades, aren't we? You could pick anything. You could pick 6, 4, 2, 0, -2 or something. You could throw in any kinds of numbers there. So it's kind of an arbitrary assignment of numbers to these letters. And so even though we give them numbers, they still represent ordinal kinds of values and not interval or ratio, which brings up then the question, if that's the case, then what's a grade point? Does a grade point really mean anything? You shouldn't be taking an average when it comes to qualitative data. So maybe a sense of measure of the middle, or central tendency that we'll talk about later in Chapter 3, maybe a more appropriate sense of the center would be to look at maybe the mode. What is the grade A, B, C, D, or F that comes up the most often? And maybe we should use that for a sense of the middle, or a typical grade, as opposed to concocting a grade point. So I just thought that was an interesting aside. Let's see. Let's see, with ratio data that is interval, but you can divide one value by number. Height, weight, distance. Okay, no, nothing else I wanted to say there. I think something was bouncing around in my head, but I think that's good enough. So we have families of numbers. This, again, I think is quantitative in nature. It's not in the slides, but the author talks about quantitative values can be broken into two types, discrete and continuous. That's not something we do with qualitative data, but quantitative, which would be interval or ratio data, could be discrete or continuous. And I like how the book puts it. Discrete data is typically counts of things. So if you're collecting data that's basically about counts of things, like maybe the number of students in each class on campus at a particular time, then that would be discrete data. But if you're measuring something, then that's continuous. Or if you can think of a continuum. So there's a continuum of values, whereas discrete values are very specific. So for example, integers are an example of discrete numbers, where you have 0, 1, -1, 2, -3. Those are all discrete from, they're all separated from each other, and there's nothing in between. I like how the person I got the slides from here says no in-betweenies. That's discrete values. There's no in-betweenies with discrete values. And that's why the idea of counts makes a lot of sense. So if you're counting stuff, then you're looking at discrete. If you're measuring things, then when you measure, you have a continuum, and so you can get all kinds of values when it comes to having to measure something, like with a tape measure or a scale of some kind. And so those would be continuous values, weight, height, distance. Those kinds of things are measured, and so are continuous kinds of numbers. So breaking up quantitative values, counting numbers are the discrete values. And typically they're integers, whole numbers. Whole numbers are the counting numbers with 0. Natural numbers are 1, 2, 3, 4, etc. The counting numbers. No in-betweenies. Measuring numbers are fractions, decimals, scientific notation. For any two distinct different numbers, there's always another such number between them. So for example, with discrete, between 1 and 2, there are no other discrete values between 1 and 2. But if you're looking at a measuring number or continuous type number, between 1 and 2 is an infinite number of those kinds of numbers. So 1 1/2, 1 3/4, 1.3658, 9, 10, or 0, etc. Could have all kinds of values between two continuous values. Okay, and that finishes up I think a good sense of what the content is of 1.1. So again, try those homework problems. The textbook has all the odd answers, and I have the evens. So if you are interested in looking at some of the even answers, shoot me off an email and in Canvas, and then I can go ahead and talk to you with it. Or again, you can use the Canvas email system between other members of the class, and so you can go ahead and you can discuss these kinds of things with each other. I like it when students get together and talk about the content of the course and try to help each other out. I think that's a very valuable thing to do. Okay. So, yep, I'll go ahead and stop there. I don't think there's anything else I wanted to add. But this is, I think what's rattling around my head here is this is the first video for all the sections that we're going to be doing, and this is what I kind of do in class. So I'm trying to make it as much like I do in class in terms of the lecture videos. I do this kind of thing. I take these slides, these PowerPoint slides, and I go through them and just try to sort of expand on what's in the slides. So that's what I do in class. So hopefully this will work out well for you in this online kind of a setting.